Hey guys, we're back here to discuss a new unit on exponential functions and how we can transform these types of functions, what key features they have, how to graph them eventually and find tables. And then we're going to look at inverses of functions in a little bit, separate video also as well. So where we're going to begin today is first by just noting that an exponential function generally has this form up here. So it always has a variable exponent. And of course, if it has an exponent, then it has a base as well. And we just want to make sure that whatever number comes in front, if we have a transformation, that we want to make sure that number is not equal to 0. So mainly, it's a function that has a variable exponent and a simple base. So what we're going to see first is how we can transform these types of functions. We've talked about transformations quite a bit now. We did that in the context of general functions at the beginning of the semester, and we also talked about how we can transform square and cube roots. Now we're going to look at how to transform an exponential function. And the first thing we're going to do is to identify the parent. So this is actually a child or a transformed function, right? There's a lot of things going on here. But the parent is pretty simple. Okay? The parent is always the simple base with a simple variable exponent. So in this case, exponent will be x. That's always the case. The base just depends. What is it that has the exponent or possesses the exponent here? And it turns out that 4 is the base. Okay, 4 to the power of x. The base is 4, simple base, simple exponent. That is our parent. Now, things around that have changed, right? If you remember your A's, B's, H's, and K's, that's what we're looking for here. And for exponential functions, we're really going to be focusing on A, H, and K, not so much horizontal stretches or shrinks or y-axis reflections. Those can happen, but those won't be the focus of our unit. So in this case, we do see that A has changed, right? We do have a x-axis reflection, meaning if you compare this function, the parent, to its child, one of the differences that you'll see is that it's been flipped upside down over the x-axis. That's because of this transformation here. So I'm going to go ahead and check this one off. Okay. Another transformation is that we're multiplying by 3. That's a number that's larger than 1. That's where A is. So we have a vertical stretch by a factor of 3. Okay, if it was a number less than 1, some sort of fraction less than 1, then it would be a vertical shrink, right? The graph of the parent will get taller in this case. It's going to be stretched out as well as flipped. Something else that's happening is we're changing h, the number next to x that we're subtracting by here, means our graph will shift to the right by 5 units. Okay, compared to the parent function, this graph would shift right by 5 units. And lastly, we change k, adding off to the side, finally means we have a transformation or a shift up 6 units. Okay, if we subtracted off to the side, we would be moving down. If that was -6, that'd be a shift downward. If we added next to x, then we would be moving to the left. So what I would always recommend, and I've done this in the past as far as recommendations, graph your parent, graph the child. You'll be able to see the differences, and these descriptions should match the differences that you see when you compare those graphs. So that's one thing that you need to know about exponential functions, how to interpret transformations of them. Something else that we'll talk about next is growth versus decay. So all exponential functions either grow or they decay. So what does this mean? For growth, the way that we can identify that is by looking at the base. So think of your parent function, what's the base? If the base is larger than 1, it's going to be a growth. Okay, we're going to see something that either rapidly increases towards the right or rapidly decreases towards the right. Whatever type of movement that happens with your graph either goes up very quickly or it goes down very quickly. Okay, that's a key word there. And the shape of the L, sorry, the shape of the graph here will be like a backwards L, okay, or an upside down backwards L. A decay, on the other hand, will have a base that has a number less than 1, so some sort of fraction, right? And in this case, a decay will look like it flattens out like a normal L shape, right? This graph kind of looks like a normal L. It flattens out towards the right-hand side of the page. And even if we flipped that, right, maybe it got reflected, it still flattens out. Okay, that would be an example of growth versus decay. Now, something else that all exponential functions have, I'll leave this off to the side, is horizontal asymptotes. Okay, these are where the exponential function is going to flatten out at some point, and it's like an invisible barrier that the graph will never cross. For example, you want to check your up and down transformations. That will tell you where you have a horizontal asymptote. Every single graph will have one. Every single function will have one. And in this example on the left, right, we have this function, 2 to the power of x plus 3 off to the side. So the horizontal asymptote in this case is going to be y equals 3. The graph will look something like this. Okay, it's an example of growth, right? We have something that is a base higher than 1. So this is an example of exponential growth. It rapidly rises, and it will never go lower. The graph will never show up on or lower than this dotted line. This dotted line is our horizontal asymptote. The graph will never cross that. It will never touch it. It will get very close to that dotted line, but will never actually cross that barrier. And if we had minus 3 then, that would mean our dotted line should show up below the x-axis, of course, right? Y equals negative 3. That would be our horizontal asymptote. It cuts across the y-axis. Once again, it would be the shape of a backwards L. The graph will get very close to that dotted line, won't actually cross it. And in the middle, okay, it doesn't look like there's a horizontal asymptote at all, right? It doesn't move up or down, but there still is one. And if you don't move up or down, that must mean at the, or along the x-axis when y equals 0, okay? It's almost like we're adding or subtracting by 0 off to the side here. There's no transformation up or down, therefore y equals 0 has to be your horizontal asymptote. Once again, all exponential functions have them, even this type of function, where it's equal to 0. So there is a dotted line, it's just along the x-axis. The graph will never touch the x-axis or go below it. Okay, so that would be horizontal asymptotes. And one more type of key feature I want to talk about in this video will be domain versus range, okay? Because that is very closely related to asymptotes. I think it's a good follow-up. Exponential functions have a domain that's always the same. The graphs will show up everywhere to the left side of the page or the graph and everywhere towards the right. So all real numbers, you can plug any number into x for an exponential function, always negative to positive infinity. Okay, you can plug any number into x for whatever function you're given. I could plug in 1,000 here, or negative 1,000, or 0. I can always plug in a number and I will get back something that's a real number. The range though, right, what can you get back when you plug in a number? It just depends, okay? And it depends on two different things. Number one, it depends on what asymptote you have. And remember, every exponential function has that. It has a horizontal asymptote. And number two, it depends on what direction your graph is headed. Is it headed upwards or downwards? So domain, remember, is from left to right. Where does the graph show up? In this case, it shows up everywhere. For the range, that means look at the graph from down to up. Where does it show up? It's going to be restricted, and here's an example. We have f of x equals a to the power of x plus 4 minus 2. Remember, that's the value of our horizontal asymptote, right? Y equals negative 2 is like an invisible barrier. The graph will never cross that. So if we actually do graph this function, right, it might get close to that orange dotted line, but it's never going to touch it, never going to cross it. Okay? And that means our domain, always the same for exponential functions. Range, though, okay, the graph heads upwards towards infinity. And where does it head upwards from? It heads upwards from -2, that horizontal asymptote. Okay, so asymptote, direction of the graph, up versus down, those are always going to be the two things that you'll use to determine the range. Okay, so that's the last key feature, and I want to tie this all together by finally mentioning one last thing, and that's that we have a special number now that we're going to encounter a bit this week, a bit more next week, and then especially in our next unit, we're going to explain what this is useful for. But just like you have had pi in the past, or imaginary number I, e is a special number. It's a non-repeating decimal, and it's bigger than 1 is the important thing here. Okay, so if we were going to be given a function, for example, and asked to find our normal, transformations, what's the parent, growth, decay, etc. Okay. Treat it like something normal. This is the base, e, right? So if you wanted to name the parent would be, let's say g of x, it should have a different name, equals e to the power of x. That would be the parent of this child, okay? And we know that this should grow, not decay, because it's a number bigger than 1. That base, bigger than 1, and the graph shows that it rapidly decreases, so it does grow in that sense. Transformations, same as usual. We have a reflection over the x-axis, or across the x-axis. We have a vertical shrink in this case, right? 3/8, that's less than 1. By a factor of 3/8, we have shift to the right, sorry, not to the right, to the left, excuse me. So we're shifting left by 2 units. And finally, we should be shifting up 1 unit because we changed k, whereas here we changed h. So don't confuse your h's and k's. Shift up 1 unit, shift left 2 units, and then compare your graph, and it should match what you have here. Excuse me, that should be at 1. But everything else should match, and it does. Okay, it shifted left 2, up 1. And that means the horizontal asymptote, if we look at k, right, if we look at the number off to the side, that's going to be y equals +1. The graph will never cross that line. It's been flipped over the x-axis, right? It has been moved left, it has been moved up, it has been shrunk compared to what the parent would look like, and we have this dotted line at y equals 1, horizontal asymptote. Domain, all real numbers as usual. Graph should show up everywhere left and right off the page. And then finally, range comes from 2 different things, right? It comes from your asymptote and what direction is the graph headed. In this case, it's headed downward. It's headed downward towards negative numbers, towards negative infinity, upwards towards, but never crossing, that asymptote of 1. Okay? Parentheses there because it never crosses the asymptote, never touches it, and it only approaches infinity, it never actually reaches it. So that wraps up the lesson for today. We will come back in our next lesson and talk about 2 more key features, intercepts and end behavior, as well as how you can create tables and graph for these types of exponential functions. So I will see you then.